Okay, so after lunch, there is higher probability that someone will fall asleep. Don't worry, I will not wake you. Whenever this happens, once in a while, I remind my students of a story that happened in Tel Aviv University when one student fell asleep and the lecturer told the student next to him, please wake him up. And he said, the one who made him sleep, he should wake him up. So I will try not to make you sleep. Okay, so Nir, which is, by the way, my academic father, he was my supervisor for PhD, talked about lock-based data structures. And now we will try to break out of these locks and to see what we can do if we would like to synchronize our concurrent algorithm without having to use locks. So Nir told us about this. I will now talk about non-blocking algorithms. It is a wide class of concurrent algorithms. I will actually be more specific and talk about a specific subclass called lock-free algorithms. And then later in this mini course, Maurice will describe yet another paradigm for concurrent synchronization called transaction memory. So we are now delving into this area of non-blocking algorithms. So just to recap quite quickly, what is the problem with lock-based programming, or what is the trade-off? So on one extreme, we may use what is called coarse-grained locking. So we may protect the whole data structure using a single lock, or full procedures using a single lock. So the advantages are clear. It's very easy to program such code when you protect it with a single lock. It's very easy to prove that the algorithm is correct because it's essentially sequential. But this is also the disadvantage. If it is sequential, then it will not scale. There's no concurrency, no real parallelism here. So this is the problem with coarse-grained locks. And at the other extreme, we have fine-grained locks. So we can either protect every small data subset of our data structure with a lock, or protect very small portions of the code. And this is more scalable. Indeed, many program in this manner. It can yield good performance. But on the other hand, it's not robust enough. So if one thread is very slow while it is holding the lock, then other threads will be slow as well. You often do not want this situation. And if you really need a robust system where every thread continues to make progress, although the other threads may die when they hold the lock, then you need another mechanism. You cannot use locks. And also, as we know, when we have many locks, then we have to synchronize very carefully what locks we capture in what parts of the code and what is the order that we capture these locks, because otherwise we will end up having problems such as deadlocks, priority inversion, and convoying, known problems of lock-based programming. So we would like to be able to synchronize without having to use mutual exclusion locks. So there is a large class of algorithms called non-blocking algorithms, which permit us to do that. And in the literature of concurrent programming, we actually identify 3 subclasses within this large class, and they are ordered here according to the level of difficulty of implementing them. So implementing weight-free algorithm is notoriously difficult, and as we go down here, it becomes easier to implement these types of algorithms, but on the other hand, the progress guarantee that they provide us get weaker and weaker. So let's start with the class of weight-free algorithms. Rashid will talk about this class actually tomorrow. With this class, every thread is guaranteed to make progress. So if a thread is performing some high-level operation on the object, for example, a push or a pop on a stack, or a fetch and increment operation on a counter, and in order to do that, the process does more and more steps, such as read or write or compare and swap, then if the algorithm is weight-free, we are guaranteed that after some finite number of steps, the operation will terminate. So we have individual progress for every thread, and this is a very strong progress guarantee. So such an implementation is robust. But on the other hand, often they are very difficult to program. So this is the main trade-off here between programming difficulty and the level of progress that we gain. By the way, stop me at any stage if you have questions. Don't defer them to later on. Log-free algorithms, and this is the class of algorithms that we will focus in this mini course, provide a weaker guarantee. They only guarantee global progress. This means that if processes take more and more steps, again, each step is a read or write or compare sort or whatever, then some operation manages to complete. But any specific thread may starve, may not be able to complete its operation. So does these two progress guarantee remind you something, some notions related to log-based programming? In terms of the relation between wait freedom and log freedom? Is? Okay, so log freedom is more fair in a sense. Let us recall the progress guarantees that exist when we talk about logs. So in a logs, it's a different model. When we discuss logs, we assume that processes do not fail. And there we discuss deadlock freedom and starvation freedom. Are you aware with these concepts? Okay, so deadlock freedom in the context of log-based programming guarantees global progress, that eventually some process will enter and then exit the critical section, similarly to log freedom. And wait freedom is more or less equivalent to starvation freedom. Starvation freedom also guarantees individual progress. Every process that wants to enter the critical section will eventually enter it. So, once again, we have these two notions. And why is it true that if an algorithm satisfies this property, then the algorithm does not use logs? Okay, so let's relate it to this. Let's look at this definition. Even if thread A fails while it holds a lock, we are guaranteed here that every other thread will be able to complete its operation. So this means that a wait-free algorithm cannot use locks, because if the algorithm uses mutually exclusive locks, then if one thread dies while holding the lock, other threads cannot make progress. So if our algorithm satisfies this property, the algorithm is wait-free, or even lock-free, then this means that it does not really rely on mutual exclusion locks. So if our algorithm satisfies either one of these conditions, then it means it can synchronize without the use of locks. Is this clear? Okay. And a third, even weaker condition is called obstruction freedom. And this condition only guarantees that a thread will make progress while performing its operation if it runs sufficiently long without any contention. So if thread A performs a read, then a write, then another read or write or whatever, a long sequence of steps, and in this time no other thread takes any step, then eventually thread A will complete its operation. If the algorithm meets this requirement, then the algorithm is obstruction free. And it can be seen that also this condition precludes the use of locks. So if an algorithm is obstruction free, then it synchronizes without using locks. One more thing to observe here is that there is a relation between these three classes. So what do you think is the relation between the class of wait-free algorithms and log-free algorithms? There is a containment relation. this class is wider than this class, because if an algorithm is weight-free, that is, if it guarantees individual thread progress, then it's easy to see that it's also log-free. It also provides global progress, but the converse is not necessarily true. An algorithm can be log-free, but not weight-free. And we will see examples of such algorithms in the rest of this talk. So questions up to this point? Okay, so now let's focus on the middle class out of the three that we saw, on the class of log-free algorithms. As I said, they ensure global progress, and since we do not use locks, we are not susceptible to the problems of using locks such as deadlock and priority inversion. On the downside, we often need to use stronger synchronization operations, not just reads and writes, but also compare and swap, fetch and add, swap, test and set, whatever operations that are read, modify, write operation. That is, they atomically, all these operations atomically read a value and then write a new value based on the read value. And they are also often quite difficult to devise and prove correct, maybe not as much as weight-free algorithms, but certainly much more complicated than just using sequential code. Okay, so what we will do from now on until the end of this mini course is to see a sequence of a few algorithms. We'll start with two relatively simple algorithms. One would be an implementation of a stack. Then we will try to argue that the implementation is correct, and we'll suddenly realize that we need some new definitions in order to define what is a correct concurrent algorithm. It's not obvious, as we will see. And then I will describe another log-free algorithm implementation of a queue due to Maged Michael and Michael Scott. And then we'll see two more complex algorithms. We'll see Maged Michael's linked list algorithm. And then, if we will have sufficient time, we'll see a more parallel implementation, log-free implementation of a stack that is based on the notion of elimination. Okay, so let us start. In the mid-80s, IBM, in one of its manuals, published a relatively simple algorithm that was used to exemplify, meant to exemplify how we use the compare and swap operation that was introduced more or less at that time. And later on, a researcher named Treiber published a variant of this algorithm, so the algorithm is called the Treiber/IBM stack algorithm. I'll just call it the Treiber algorithm. And the idea is very simple. As you recall, a stack supports the last in, first out semantics. So the last item pushed into the stack will be the next item popped from the stack. And Treiber's idea was to implement the stack simply as a linked list. So every item in the linked list contains some value, which is the application value, and a pointer to the next node. And there's also a shared variable called top, which points to the node at the top of the stack. Or if the stack is empty, then the value of top is simply null. So in order to perform operations on this stack, the top pointer is being manipulated using compare and swap operations. So compare and swap, you are familiar with it, but still a quick reminder, when it operates on some variable var, it receives two argument expected value and new value, and then it atomically does the following. It reads the current value of the variable. If it equals the expected value, then the value is swapped, the new value is being written, and a success indication is returned. Otherwise, a failure indication is returned and the variable is not modified. So the idea is that you can read a specific value, compute some function based on this value, and then write the new value only if the older value did not change. So there are some reservations to what I said now regarding CAS, which will be discussed later in this course when we will talk about memory reclamation. But let's move on for now. So this is CAS. So how would the push operation proceed on this simple stack? Well, in order to push a new item to the stack, we first, when we will see the code in a minute, the pseudocode, we first create a new node, storing the value that we want to add to the stack. We point this new node to the current top element, okay? And now in order to complete the operation, we would like to perform a CAS to the top shared variable, and if its value did not change since the time we read it, then it will now point to the new element that we added, which will be the new top of the stack. So that's the very simple idea underlying the logic of the push operation. So let's see the pseudocode. In a C-like syntax, the emphasis here is not on the syntax of the pseudocode, but rather on the algorithmic ideas. So when we do a push of some value v on the stack S, a capital S, then as we saw before, we start by creating a new node, a reference to which is stored to variable n. Then we write to the val field the value v, the argument, which is the value we would like to add to the stack. And now, in an infinite loop, we do the following in every iteration. First, we read the current value of the top pointer. Then we set the next pointer in the node that we created to point to the current top. And finally, we do a concurrent swap that atomically tries to swap the value of S from the previous value to the new node that we created. Now, let me remind you, well, I guess you know it already, that concurrent swap returns a success or failure indication. So if concurrent swap succeeded, then the operation returns. Otherwise, it will perform another iteration. But why should the push operation fail at all? What may cause it to fail? Yes, if between the time where we read top in line 4 and until the time where we try to perform the concurrent swap, another thread managed to change top, then the concurrent swap will fail because the value of top will not be the previous value that we read anymore. It will not be the expected value, expected argument of the concurrent swap operation. So a thread that tries to perform the push operation may perform more and more iterations, but never succeed in adding its item, right? So how do we know that there's any progress with this algorithm? Excuse me? Yes, so indeed the explanation is that there is progress is that if some operation, some push operation fails in every iteration, its concurrent swap fails, this can only be because another thread concurrently, that is between line 4, the execution of line 4 and the execution of line 6, another thread succeeded in modifying the top pointer, which means that this other thread actually succeeded in performing its operation. So if this thread starves, it starves because it's not able to complete even a single operation. This can only be because other threads in the same time continue to complete more and more operations. And this means that we have global progress. This means that the algorithm, well, we did not yet see the pop operation, but you will see it soon. This means that the algorithm provides us with lock freedom. I remind you that lock freedom means that there is global progress, but individual threads may starve. So any questions up to this point? Yes. Yes. The question is, can we assume that the compare and swap operation is strong in the sense that if the value changes from some value A to B and then back to A? No. Okay. Okay. I see. So the question is whether this implementation will work even if there are spurious failures, namely situations in which the case should succeed, but it fails. Well, assuming that at least once every k for some k such cases, the case will operate according to the semantics that I showed, this algorithm will still be lock-free. More questions? Yes. Yes. Okay. So I guess what you're asking refers to what is called the ABA problem, which means that we read the value of the variable which we would like to apply cas to. In our case, this is the top variable. We see some value B, some value A, sorry, but then the value changes from A to B and back again to A. So this, in a sense, defeats what we would like to get from the semantics of the compare and swap operation. We would like to get from it the guarantee that we manage to perform the swap only if the value did not change since when we read it, in this case, here in line 4. So this actually is a problem with compare and swap. And in our context, this means that we need to be very careful when we recycle structures that we use in the stack. So in the algorithm I'm presenting to you, let us assume that there is no recycling of nodes. So you will never see two pointers in the top variable that are the same. Later on, there will be a talk about memory recycling and the way that we may reuse, for example, nodes, structures that we allocate and then are able to use again and again. We will see how this can be done without running into this problem that you asked about. Yes. Mm-hmm. Okay. More questions up to this point? Okay. So let's see the pop operation. It's also quite simple. And the idea is that since we are following the last in, first out semantics, we would like to take this value. So what a thread does when it wants to dequeue is to simply try and change the value of top using compare and swap so that instead of pointing to the current top, it will point to the next node. And once it succeeds in doing that, the thread can take this value and go off its way. This will be the return code of the pop operation. So let's see the pseudocode. Again, the pseudocode is an infinite loop because the compare and swap that is being applied to the top pointer may fail again and again. Yes? Ah, okay. Better? Yeah. Okay. Sorry about that. So returning to the pop operation, it proceeds in infinite loop, where in every iteration, the thread first reads the current value of the top pointer. If the top is null, then the stack is empty. So the pop operation returns an empty indication in such a case. Otherwise, as we saw in the previous slide, the thread attempts to perform a compare and swap that will atomically change the value of the top index from its current value to the value of the next node. So this is top.next. Okay? Again, if we succeeded, then we can return the value that was stored at the topmost node, which the value is being read here. And this line here hints to the fact that it is not in general true that we may at this stage recycle or use for other purposes the node from which we just extracted the value B. Erez will discuss issues like this on Friday, how garbage can be collected, because it may be that other threads are currently looking at this node, or maybe about to apply an operation, read or write to this node, so it's not simple when we can use it again. So this is just to let you know that there is an issue here, but we disregard this in this discussion. We assume that there's no problem of garbage collection. Maybe the language, the runtime environment does this for us, or maybe we just don't recycle. And finally, the value can be returned. So also here, we can see that the progress guarantee of this algorithm is global. Namely, a single operation may fail again and again. The compare and swap here may fail in every iteration because it might be, maybe it's not probable, but it's possible that in every iteration between the time when we read top in line 2 and the time when we try to perform the compare and swap in line 5, some other thread manages to change the value of top. So we will fail, but if we fail, this is only because another operation succeeded to change top. So another operation will succeed in completing. So we do have global progress. Okay, so any questions regarding this algorithm or why it is lock-free? Okay, great. But now we should ask ourselves about this algorithm, whether it is correct, or in what sense is the algorithm correct. Okay, it provides lock freedom, but does it really provide us with the semantics of last in, first out stack? In order to do that, this we already saw, in order to do that, we need to take a step to the side and consider what does it mean for a concurrent algorithm to be correct. It's not clear what the definition is, and indeed there are many definitions for what it means for a concurrent algorithm to be correct. All these definitions extend in this way or the other the notion of a correct sequential algorithm. So for example, for a last in, first out stack, we know what a correct algorithm is, a correct sequential algorithm is. We simply have a total order on the push and pop operations, and we know that a pop operation should return the latest item that was added to the stack, or empty if the stack is currently empty. But this assumes that we know the total order, that we have a total order of operations on the data structures. When we discuss concurrent algorithms, there's no total order anymore because we have concurrent operations and we can't say which of these operations comes first. So the definition becomes complicated. And what we will see now is actually a motivation and then the definition of a correctness condition, which is called linearizability. Okay, one of the key difficulties of this condition is to say the name linearizability. It takes some practice. Anyone wants to try linearizability? No one wants to try. It's okay. Okay, so let's see what this definition means. In order to do that, let's first consider the correctness of a sequential object, a simple object, a counter, which only supports the fetch and increment operation. So if we consider a sequential counter, then we expect the counter to return contiguous integer values starting from, say, 0. So the first call to fetch an increment will return 0, the next call will return 1, then 2, etc., etc. But the question is, if the algorithm that implements the counter, if this is a concurrent implementation, then what does it mean consecutive operations? Consecutive operations means that every operation on the counter terminates before the next operation starts. But in concurrent executions, this is not the case. We have concurrent fetch and increment operations applied to the counter. So how can we define what a correct implementation is? So this figure here should make this problem more concrete, maybe. Each invocation or each execution of the fetch and increment operation is not just one step. It is in general a series of steps which can be read or write or compare and swap until the operation terminates. So each fetch and increment operation on the counter is actually extends over an interval of time. And we say that each such operation starts with an invocation when we call the operation on the object, and it ends with a response. In our case, the response is the integer value returned by the fetch and increment operation. Now, as we can see, or maybe let's say this explicitly, if we have two operations such that one ends before the other completes, then we say that this definition precedes that operation. But we also have operations in general whose execution intervals overlap. In such cases, we cannot say which operation precedes which operation. So we need to define what it means for an implementation, a concurrent implementation that can yield such executions. We need to be able to say when the execution is correct, it is a correct execution of a concurrent counter, and when it is not. So let's make this example more concrete. Assume that we have this execution, and in this execution we have 4 operations of fetch and increment that return these values, 0, 1, 3, and 4. So it should be clear that this execution is illegal. Because after all these 4 operations terminate, we do not get a contiguous range of integer values. We would expect to receive 0, 1, 2, 3, etc. But there is a jump here between 1 and 3. So this is incorrect. Okay, so let's see another possible execution of a concurrent counter. In this case, the values that are returned by the 4 operations are contiguous number, 0, 1, 2, and 3. So there are definitions of correctness that will accept this execution as legal. But this execution is not legal according to linearizability, to the definition of correctness that is most widely used in the distributed computing community. And the reason is that we have here two operations. This operation on the left, for example, preceded the operation on the right, but still the value returned by this one is larger than the value returned by that one. So with linearizability, we also require that the values returned by the operation respect the order of the operations. So if we have, in this example, we have two operations, this one is strictly after this one, then the value returned by the later operation should be a number greater than the value returned by the previous operation. So here is finally a correct execution. If we see this execution, then we know that it is legal. And if all the executions of a concurrent counter are legal in this sense, then we say that the algorithm is correct. So in this execution, we have these four operations returning contiguous values from 0 to 3. And the values that they return respect the real-time order of the operations. So, for example, these three operations, each of them precedes the right-hand operation, and indeed they return smaller values. So linearability intuitively means the following thing. We can look on these four operations and find a point in each one of them, which we call the linearization point, and we assume that the operation happened atomically, instantaneously, at this point. And then we get, in this case, this order, a total order of the operation, okay, such that the values that are returned would have been returned by a sequential counter if the operation were performed in this order. And, for example, in this case, this is the first point where we assume that this operation occurs and it returns 0. This is the second operation, it returns 1, 2, and 3, etc. And since we place these atomic points inside the interval of every operation, then real-time order is maintained. So if one operation preceded another operation, then its place in the order is before the later operation. So we will see a few more examples in order for you to get a better feel for this definition. This is the formal definition. Let's skip it. It only formalizes the notion that we saw just now. So let's see more examples. Suppose we have this first in, first out queue, and we have two threads performing operations on this queue. So the blue thread performs an NQX concurrently with an NQY operation by the red thread. And then we have two more operations. First, the red thread does a DQ and gets the value X. And then the blue thread does a DQ and gets a value of Y. So far, so good? Now, in order for us to say that this execution is legal, that is linearizable, we should ask ourselves, can we order these four operations in a total order by putting a linearization point in the interval of each of these operations so that the total order that we get is a legal sequential execution on this queue. So what do you think? Yes, it is possible. For example, if we put our linearization points here, then we get a sequential execution which is correct for FIFO Q. So first we have an NQ of X, then an NQ of Y, followed by a DQ of X and a DQ of Y. So first in, first out, it's okay. So this is a legal execution, a linearizable execution. And once again, if our algorithm only generates such legal executions, then we say that the algorithm itself is correct, that is, it is linearizable. Let's see another example. So here we have these three operations. First NQ of X, then NQ of Y, concurrently, more or less concurrently with DQ of Y. So what about that? Okay, this is illegal because no matter where we put the linearization point inside the interval of these two operations, the NQ of X precedes the NQ of Y. There is an order relation between the two. So this means that it can't be that the single DQ that we have returns Y. It must return X. So this execution is illegal. Any questions up to this point? Okay. Let's see another example. Let's say we have a very long operation that does an NQ of some value X, and the operation is still not completed at this time. And concurrently, we have an operation by another thread, by the red threads, that does a DQ returning that same value. Is this legal? I heard no. Any other suggestions? Yes, indeed. Because once again, we should ask ourselves, can we find linearization points such that they do not violate the order of operations, but we only have here two operations which have no order between them. They are concurrent. So we can put it in any order that we like. And if we look at the operation in this order, then we have NQ of X followed by DQ of X. So it's okay. Is this clear? It may be a bit confusing the first time you look at it, but it makes sense. And finally, let's see another execution where we have two NQ operations that are concurrent, followed by two DQ operations that are concurrent as well. And what we should pay attention to in this example is that we are allowed to have more than one linearization order. So for example, we can choose to order this operation to think of them as if the NQs happened in this order, first Y, then X, and the DQs as well. But we may also use an alternative order in which we assume that the NQs happened in the converse order, that is first X, then Y, and the DQs as well. So it's okay if we have more than one proof, let's call it, that the execution is legal.